Welcome to Perimeters and Areas of Similar Figures. I'm Mr. Pi, the math guy, and the key thing is we're not maybe necessarily going to be calculating perimeters and areas of these shapes. We're going to be given one of those, and we're going to be asked to write the similarity ratio or the ratio of the perimeters or the ratios of the areas. And we're going to use that in some problem-solving situations. So let's get this geometry party started. Here we start to discuss the perimeters and areas of similar figures. Here we have two triangles, and we're going to say that they are similar. I'm going to label this side A, and I'm going to label this side B. To compare the areas of similar figures, you must square the similarity ratio. Well, what's the similarity ratio? If the similarity ratio of two similar figures is A to B, in this case, this side to this side, then the ratio of their perimeters is going to also be A to B. And the ratio of the areas is going to be a squared to b squared. Well, if we stick some numbers into this, we can really have what you would consider three final answers here. But if we say that this is 5 and that this is 7, the similarity ratio is going to be 5 to 7. And that would be smaller to larger, or in this case, A to B. The ratios of their perimeters is also going to be 5 to 7. Since that's a one-to-one correspondence, it doesn't change. Perimeter is just the sum of the lengths of the sides, or the similarity ratios, if you will. And here, the ratio of the areas is a squared over b squared. In this case, a squared, we could write that as 5 squared, and b squared as 7 squared. And we can simplify that by evaluating the squares, 5 squared being 25, and 7 squared being 49. So here, we found our first set of ratios, their similarity ratio, which you learned about in a previous lesson on similar figures. And the ratio of their perimeters is the same. And their areas is just the similarity ratio squared. So we're going to see how we're going to problem solve with this in coming examples. Example 1t, we're told the triangles below are similar. Because we know they're similar, we'll be able to find a similarity ratio, which allows us to find what we have to find for this problem. Find the ratio, and in this case it's very important, find the ratio of the larger to smaller of their perimeters and their areas. We need two answers here. We need the ratio for the perimeters, larger to smaller, and the ratio for their areas, larger to smaller. So we're going to start this off by writing down a place for our answers. Perimeter. And then area. And to find these similarity ratios, we have to find what combinations of these sides of these two triangles will make a proportion. And if we take a look at what I'm doing here, I'm rotating this triangle so you can visualize it, that we can see that the side 4 should correspond to the side 5. 5 should correspond to 6.25, and 6 should correspond to 7.5. And I'll just leave it like that for now. So remember, we have to do larger to smaller. Don't make the mistake because the smaller triangle's on the left. Put that in the numerator. In this case, we're saying 5 corresponds to 4, and we're writing this down as 5 over 4. Now this is the similarity ratio. And if you would have written the similarity ratio as, say, 6.25 over 5, well, that's not exactly the best similarity ratio. What you would need to do to that one is multiply it by 4 over 4. The reason I'm choosing 4 is I have a quarter here. 0.25 is a quarter, so I want to get rid of that quarter. And I do that by multiplying by 4. 6.25 times 4 does give me 25. And 5 times 4 is 20. And what you should notice is that 25 over 20 does reduce to 5 over 4. So you could have chosen another pair of sides besides 5 and 4. If you would have had some extra work to do to find the similarity ratio. Now, once we find the similarity ratio, we know the perimeter ratio is equal to 5 over 4. And that the area ratio is just the square of the perimeter ratio. So the area ratio is 5 squared over 4 squared, which can be rewritten as 25 over 16. So here we have the perimeter ratio, and here is the area ratio. We're going to see in coming examples how to use these ratios to solve problems to find areas of similar figures when we know the area of one. Example 2t, we're told the ratio of the lengths of the corresponding sides of the two regular octagons is 8 to 3. The area of the larger octagon is 320 square feet. Find the area of the smaller octagon. To do this, first off, you have to understand that this is the similarity ratio. So over here, we can say that 8 to 3, 8 feet in the larger octagon is equal to 3 feet in the smaller octagon. But we're not working with perimeter or similarity in this case. We're working with the similarity of the area. So we need to square this thing. So 8 squared over 3 squared, and that gives us 64 square feet, or 64 square feet in the bigger octagon is equal to 9 square feet in the smaller octagon. This is what we're going to use, and why we're going to use this is we're told that the area of the larger octagon is 320 square feet. What we have to find is the area of the smaller octagon. So we're going to use this area ratio and set it equal to what we have over here. And don't make the mistake, this isn't going to be A over 320. This should be 320 square feet over A, the area of the smaller octagon. And when we solve this, we can really just ignore the units to the end. We could work them out, or we could just know that our answer is going to be in feet squared. We go A times 64, or 64A, and then we do 9 times 320, and 9 times 320 is 2,880. Then we divide each side by 64, and when we do that, we find the area of the smaller octagon is 45 square feet. You have to, in this problem, this example of TT, you have to use the area ratio. You do not use just 8 over 3. You have to use 8 squared over 3 squared, 64 square feet over 9 square feet, and then get the right side of the proportion correct. Example 3T, we're told that Benita plants the same crops in 2 rectangular fields. The ratio of one pair of corresponding sides is 7 to 2. Seeding the smaller field costs $8. How much money does seeding the larger field cost? Well, first thing you should notice that we have no units here. We're not told feet, meters, or anything such as that. So we're just going to be working with numbers, and at the end, dollars is our answer. Now we're told here that the one pair of corresponding sides in these 2 rectangular fields is 7 to 2. Seeding the smaller field costs $8. Well, the key thing that you can't miss here is seeding. That word right there makes this an area problem. It doesn't make it a perimeter problem. We're talking about the area. So we need to take this similarity ratio, or this perimeter ratio, and we need to change it into the area ratio. Changing a perimeter ratio or a similarity ratio is as simple as squaring both of those numbers. 7 squared giving us 49. And 2 squared giving us 4. So this is our area ratio right here. We don't really need to calculate, and not ration, but area ratio. You get rid of that. That's our area ratio. And to solve our problem, we know that the smaller field costs $8 to seed. So when we set up a proportion here, 49 over 4, the other half of our proportion is going to be the cost. The cost of the larger field, the cost of the smaller field. And we put the cost, $8, in the denominator, and we can put an x in the numerator. Then we solve this by using cross products. 8 times 49. Well, 8 times 49 is 392. 4 times x is 4x. Doing 2 things at one time here. I'm going to divide both sides by 4. And I'm going to use the symmetric property and switch sides so that x is equal to 392 divided by 4, which ultimately gives $98. So the cost to seed the larger field is $98. Example 4t, we're told the areas of two similar pentagons are 32 inches squared and 72 square inches. What is their similarity ratio? What is the ratio of their perimeters? We're asked two questions, but what you got to understand is it's the same number. The similarity ratio and the ratio of their perimeter are the same thing. What we're given is the ratio of their areas. We're told that the smaller pentagon has an area of 32 square inches and the larger pentagon has an area of 72 square inches. What we're given in this problem is the area ratio. In the other problems, examples 2, example 3, and example 1, we were told or given information about the similarity ratio or the ratio of their perimeters, and we had to find the area ratio. Well, here we're going backwards. So to do this, what we have to do is take the square root of both the numerator and the denominator, the square root of 32 and the square root of 72. Now, to do this, we can think of, or we should think of, factors of 32 so that when we take the square root of it, we have a whole number. We need to think of perfect square factors. And the one that comes to mind for me is the square root of 16 times the square root of 2. These two factors will give the square root of 32. 16 times 2 is 32. For 72, what comes to mind is 36 and 2. The square root of 36 times the square root of 2. Now when I do this, the square roots of 2 can divide out. The square root of 16 is 4, and the square root of 36 is 6. So that gives me 4 over 6. Now this isn't the similarity ratio because 4 and 6 both have a factor of 2 in common. So when I divide both of those, 4 and 6, by 2, the similarity ratio and the ratio of their perimeters is 2/3. So correctly written, I should have two answers here. The similarity ratio being 2/3 and the ratio of their perimeters also being 2/3. So there's finding the similarity ratio when given the area ratio.